First, a quick overview of the three methods of heat transfer. Conduction is the one we'll be talking about first, and that's where warm molecules shake into colder ones and get them shaking, and then those shake into other ones and vibrate and hit the new ones, and then eventually the shaking works its way over all the way across the room. Convection is where the hot shaking molecules actually move from one side of the room to the other. And then radiation is when no molecules move. They emit radiation, electromagnetic waves that get absorbed by molecules somewhere else that warm up. The analogy that I like is that if you're trying to get a message somewhere, conduction is like if you pass a note across the room and the note goes from person to person. Convection is where you say, okay, I'm going to do this myself. If you want it done right, do it yourself, and you get up and walk across the room and deliver the note. And then radiation is like if you are like, I'll just text this note across the room, and my classmate will get it on their phone. I want to point out just one thing that might be a little confusing is that this A here, that's the area with which the hot thing is touching the cold thing. So that's like a circular area in this case. And now we get to the story, which is why I really wanted to make this video. Like so many of my stories, it's about me being silly and you learning to not do things from me telling you what dumb things I did. So when I was like 15 or 16, I had a job as a busboy in a restaurant, and everybody in the kitchen, well, there was like three people that coordinated to all quit and not show up on the same Saturday night. So they were slammed and busy on Saturday night, and there was only like two people working in the kitchen. And they were like, Mark, you're going to need to do all these things. So wash the dishes and get the bread out of the oven. And the first time I got the bread out of the 450-degree oven, I grabbed it with a rag and got the rag just a tiny bit wet. And it was too hot to handle by the time I got it from the oven to the counter. And I was like, woo, woo, that was hot, and dropped the rag. And the cooks laughed at me a little bit. And the next time the bread came up and it was ready to come out of the oven, they said, Mark, make sure Mark does it. Get Mark to do it. And so I came in and I got the rag wetter this time because in my 16-year-old mind, water makes things cold, right? So I got it even wetter, and and this time I didn't barely even get the bread across the room before I had to drop it. I basically threw it up onto the table and it was like, ow, 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 hot, hot, hot. And they thought this was really funny, even more funny. And so they kept calling me in to get the bread out, and I'd get the rag wetter and wetter and have a harder and harder time getting the bread over to the table before it burned my hand. And finally, a server had pity on me, and she said, you shouldn't get the rag wet. You should use a dry rag. And maybe you've been looking at this table over here of thermal conductivity values, and you found where water is pretty conductive compared to air. And air is mostly what's in a fluffy rag. It's mostly what's in your light down jacket, and mostly it's what makes your clothes insulating. Your clothes and jackets and bed sheets, basically, your comforters, they basically hold little pockets of air and that air is insulating because it doesn't conduct heat very well. So if you look at water, that conducts the heat from the 450-degree metal bread pan much better than the air in the rag. So my hands stayed much cooler with carrying the bread pan with a dry rag. So moving on to convection, just an interesting thing while I have you here. I went to Finland last summer, and it's cold there in the winter, and they heat using radiant heat. They don't force air all through their house. So what they can do is they can put these radiators near where they spend a lot of their time, and it heats up those areas more than the corners of the room where nobody really goes. So it's kind of is more efficient in that way. But yeah, here the hot water naturally rises, and then as it heats the room, it cools off and falls down, and it kind of gets naturally circulated through a convection current. And finally, radiation. So this equation is really an equation for power, the rate of energy transfer, just like we saw with the equation for conduction. And one of the numbers in this equation that you have to understand is emissivity. The emissivity is the fraction of radiation that an object not just absorbs but also emits. A black body, think the color black, it's the absence of. So black is the absence of light, which means that the black thing is absorbing all the wavelengths. So a black body is very good at absorbing light, and this may be counterintuitive, but that means it's also good at emitting radiation. So here's our ideal black body, and it's very good at absorbing a lot of radiation and also emitting radiation. If it's at room temperature, the radiation it emits is going to be in the infrared part of the spectrum. So it's going to be a little bit longer wavelengths than red light, a little bit less energetic than red light. And then, something with, this black body has an emissivity of nearly 1, and then something with an emissivity of nearly 0 would not absorb light and not emit a lot of radiation. So it would barely give out any radiation. It would barely absorb any radiation that came to it. So here's a great question. How do you take a picture or a photograph of a dog that's completely black? There'd be no light reflecting off of it, since it would absorb all the visible light that hits it. So I've had tricky people tell me, well, you could do like a silhouette of it or its shadow, or you could get everything behind it and then you'd see the shape of the dog. But what I'm going for is it's the thermal radiation it emits. If this dog is alive and warm and it has some temperature above absolute 0, it's going to be emitting radiation at this rate, dependent on its temperature. Notice this is temperature raised to the 4th power. That means the temperature is very, very, very influential in the amount of radiation emitted. So increasing the temperature just a little bit significantly increases the rate at which the radiation is emitted. But yeah, the point is it's emitting radiation, probably in the infrared if it's at body temperature. So you could just put on your night vision goggles, or take a night vision goggle picture of this all black dog. Okay, so hopefully you have an idea of emissivity by now. The next one in here, the Stefan Boltzmann constant, that's just always going to be this number. Not too much to worry about there. The area, that's the surface area, the total external surface area of the object. So you don't have to do any cutting cross-section like we did for area in the conduction equation. Let me just leave you with one example of finding the area A in this radiation equation. Say if you have a sphere like the Earth, then maybe we remember the quick little equation for the area of a sphere. Area should have a distance squared in it, so r is going to be squared. All right.